Assalamualaikum and a very good day we back to Dr. Zahid. We are from Group 1, Lab Station 1. We are going to present to you our lab video for ECH3902, Chemical Engineering Lab 1. We have conducted experiment 2 virtually, which is about the validation of Bernoulli equation. Before we start our presentation, I will introduce our group members. My name is Izliana Binti Muhammad Nizan. My metric number is 200224. Next, we have Hazirah Binti Abdul Halim with metric number 200890 and Nursyafiqah Binti Muhammad Isa with metric number 202728. Lastly, we have Syasya Zulaikha Binti Zakpar with metric number 203126. Without further ado, let's start our presentation.
My name is Hazirah Binti Abdul Halim and my metric number is 200890. Okay, I will be presenting the introduction part for this experiment. The title for this video experiment is Validation of Bernoulli equation. So here we have Bernoulli's theorem. This theorem is named after Daniel Bernoulli, who is the first one write this principle in a book named Hydrodynamics. It is described the relation between pressure, velocity, and elevation in a moving fluid. In this theorem, it says that the sum of pressure, the potential, and the kinetic energy per unit volume is equal to a fixed constant at any point of the fluid. And according to Bernoulli's principle, when the area available for the fluid to flow decrease, then the flow velocity of the fluid increase, and at that mean, while the time and the fluid pressure or the fluid potential energy decrease. And we can see this application of the Bernoulli theorem in air flight, baseball, draft, lift, and also sailing. And at the below, we have Bernoulli equation, the one that we use in this experiment.
Next, I will present the theory and working equation for this experiment. The relationship between pressure and velocity in fluids is described quantitatively by Bernoulli equation. Bernoulli equation states that for an incompressible frictionless fluid, the following sum is constant, where we have P plus 1 over 2 rho V squared plus rho G hash. This equation is constant, where P is absolute pressure, rho is the fluid density, V is velocity of the fluid, hash is the height above some reference point, and G is the acceleration due to gravity. If we follow the small volume of fluid along its path, various quantities in the sum may change, but the total remains constant. The Bernoulli equation can consider to be a statement of conservation of energy principle, appropriate for flowing fluids, where energy per unit volume before is equal to energy per unit volume after. As you can see on the equation below, P is the pressure energy, 1 over 2 rho V squared is the kinetic energy per unit volume, rho GV is the potential energy per unit volume. Considering the fluid flow inside a pipe with restriction, where we have 0.1 at bigger pipe diameter and 0.2 at the restriction part, which have smaller pipe diameter, area at 0.2 is smaller than area at 0.1. Hence, at 0.2, velocity increases and the pressure decreases. This pipe restriction causes the pressure drop, hence increase the fluid velocity. Bernoulli equation usually labeled with the term Bernoulli effect, which is the reduction in pressure occurs when the fluid speed increases. When a fluid flows into a narrower channel, as you can see in the middle of the pipe, its speed increases. That means its kinetic energy also increases. As a result, the pressure will drop in a rapidly moving fluid, whether or not the fluid is confined to a tube. However, this Bernoulli equation is limited to cases for steady flow. In this virtual experiment, for the working equation in this experiment, we have to consider flow at two sections in a pipe where Bernoulli equations for flow in pipe may be written as V1 squared over 2G plus P1 over rho G plus Z1 equal to V2 squared over 2G plus P2 over rho G plus Z2, where V1 is inlet velocity, V2 is the outlet velocity, P1 is the pressure at the inlet, P2 is the pressure at the outlet, Z1 and Z2 are the heights from reference point of inlet and outlet, where in this experiment, Z1 is equal to Z2. That means no height changes. And P over rho G is equivalent to hash that indicate the pressure head. That's all. I will pass to the next person.
Hi, my name is Nursyafiqah Binti Muhammad Isa. My metric number is 202728. Materials that we will be using in this experiment. The first equipment that we will be using is virtual Bernoulli theorem, demonstration apparatus, and stopwatch. For the methods, the first thing we have to do is use the link on Putrablast to access the O-Physics iterative physics simulation. Then, the first parameter that we will be varied is V1 and other data will be constant. This process will be repeated by changing the variable to H2 and R2 and all the data will be recorded.
Hi, my name is Syasya Zulaikha Binti Zakpar and my matrix number is 203126. Now I will proceed to present about the result and discussion of this experiment. Based on our objective, which is to investigate the validity of Bernoulli equation, we run the experiment virtually to do the simulation, and we are required to vary 3 parameters and fix the other parameter. And the parameter to be varied, the first one is inlet velocity. Okay. For this experiment, we run this for 5 times to get 5 different values. So the data we observe, which is the inlet velocity, is 1 until 5 milli per second. So the outlet pressure, which is P2, we get is constant, which is 750 kilopascal. For the outlet velocity, based on the equation of V1 equals to V2, so the V2 still remain constant, which is from 1 until 5 milli per second. For other parameter, which is P1, we get 750 kilopascal. Inlet height, which is H1, 2.5 meter. Outlet height, 2.5 meter. Inlet radius, 0.75 and outlet radius, 0.75. Based on this data, we can plot the graph, which is the graph varied parameter against P2 and V2. Okay, the first graph, which is Figure 1, graph of outlet pressure P2 versus inlet velocity. And for the Figure 2, graph of inlet velocity V1 versus outlet velocity V2. Second, the parameter to be varied is the outlet height, which is H2. So we run the experiment 5 different times to get 5 different values. So the outlet height H2, we get from 5 until 1, which is 5, 4, 3, 2, and 1. So the outlet pressure P2 is 725.5 kilopascal for 5 meter, 735.3 kilopascal for 4 meter, 745.1 kilopascal for 3 meter, 754.9 for 2 meter, and 764.7 for 1 meter. And the fixed parameter, which is outlet velocity V2, we get 3 meter per second. So the other parameter is still same with the first parameter, which is P1 equals to 750 kilopascal. Inlet height is 2.5. Inlet velocity is 3 meter. Inlet radius 0.75. Outlet radius 0.75. So the graph that we can plot, which is the Figure 3, we can see the graph of outlet pressure P2 versus outlet height H2. And the Figure 4, which is graph of outlet velocity V2 versus outlet height H2. And last, the parameter to be varied, which is outlet radius R2. So we run this experiment with 5 different values, which is we get outlet radius R2, we set from 0.5 until 0.9 with increment 0.1. So the outlet pressure for 0.5 meter is 731.7 kilopascal. For 0.6 meter, we get 743.5 kilopascal. For 0.7 meter, we get 748.6. For 0.8, we get 751 kilopascal. And for 0.9, we get 752.3 kilopascal. So the outlet velocity, which is V2, we get from 6.75, 4.69, 3.44, 2.64, and 2.08. And then the graph that can be plotted, which is figure 5, you can see the graph of outlet pressure P2 versus outlet radius R2. And the figure 6 is the graph of outlet velocity V2 versus outlet radius R2. Based on the data that has been recorded and also the graph that has been plotted, I will proceed with our discussion from this experiment, which is according to Bernoulli's theorem, as increase in fluid velocity is accompanied by a decrease in static pressure or a decrease in fluid's potential energy. Bernoulli's theorem can be generalized to various types of fluid flow, resulting in various forms of Bernoulli's equation. Different types of flow result in different forms of Bernoulli equation. So based on this experiment, it is very crucial to relate the relationship between the pressure of the liquid flow, the height and radius of the tapering circular duct, and the velocity of the liquid along its flow according to Bernoulli's principle. So based on our first varied parameter, which is the influence of changes in inlet velocity V1 to the outlet pressure P2 and velocity V2. So the table 1 shows the value of outlet pressure and outlet velocity of liquid water flowing through the tapering circular duct with 5 different values of inlet velocity. So the tabulated data was plotted into graph for further analysis. So based on the graph that has been plotted, we can see the graph of P2 versus V1. It can be concluded that the relationship between two variables is equilibrium. This is because our value P2 is remain constant throughout the experiment. And from the graph V1 versus V2, it can be concluded that the relationship between two variables is directly proportional. We can see that the value of V2 increased as V1 increased. The second one is the influence of changes in outlet height H2 to the outlet pressure P2 and velocity V2. So from the table 2 shows that the value of outlet pressure and the outlet velocity of liquid water flowing through the tapering circular duct with 5 different values of outlet height. So the tabulated data was plotted into graph for further analysis, which is we can see from the graph of P2 versus H2, it can be concluded that the relationship between two variables is directly proportional. This is because our value P2 is increased as H2 increased throughout the experiment. And from the graph of H2 versus V2, it can be concluded that the relationship between two variables is equilibrium. You can see that the value V2 remain constant as H2 increase. Next, for the influence of changes in outlet radius R2 to the outlet pressure P2 and velocity V2. So the table 3 shows the value of outlet pressure and outlet velocity of liquid water flowing through the tapering circular duct with 5 different values of outlet radius. The tabulated data was plotted into graph for further analysis. So what we conclude that from the graph of P2 versus R2, the relationship between two variables is exponentially increased. This is because value P2 is increased as value of R2 increase. And from the graph of R2 versus V2, it can be concluded that the relationship between two variables is exponentially decreased. We can see that the value of V2 decreased as R2 increased. Okay, that's all from me. Now we'll pass to the next member to talk about conclusion and recommendation.
So for the conclusion and recommendation part, the aim of this experiment was to investigate the validity of Bernoulli theorem as applied to flow of water in a tapering circular duct by using a virtual wet pipe. The varied parameter given to our group is velocity, height, and radius. For the first experiment, we changed the V1, and the conclusion is V1 equal to V2. P1 is equal to P2 when the P1, H1, H2, R1, and R2 fixed. For the second one, we changed the H2 value, and for the result is as the H2 value decrease, the P2 increase while the V2 is constant. For the third experiment, we change the R2 value, and as a result, when R2 value increase, the value of P2 increase and the value of V2 decrease. Based on the test result, it is shown that Bernoulli theorem is valid to apply in the problems given. So for the recommendation, we recommend to increase the number of trial for this experiment in order to increase the accuracy for the result. I think that's all from us. Thank you.